Hi everyone, this is Andrew. I wanted to put together a video for number 4 on the homework, the one about using mathematical induction. This is now my, I think, third time trying to record. I'm still getting used to the whole formatting and stuff, and I'm struggling a little bit, so I'm probably going to be all over the place, a little sloppy, but hopefully this does help you some. So number 4, you can see it on your homework sheet. We essentially, in number 4, here's our claim for number 4. Let me write that down. Our claim is that if z equals r cosine theta plus I sine theta, and n is an integer with n greater than or equal to 2, then z to the n equals r to the n cosine of n theta plus I sine of n theta. So like I said, we're going to be using mathematical induction to show this. So let me just start right into the proof here. Let me restate what we're trying to prove. At the start of the proof, it's always good to indicate what you're trying to prove and how you're trying to prove it. So I'm going to say that we will use mathematical induction to show that if z equals r times the quantity cosine theta plus I sine theta, and n is an integer with n greater than or equal to 2, then z to the n equals r to the n cosine n theta plus I sine of n theta. So that's what we're trying to prove. And in mine, I started by assuming that z equals r times cosine theta plus I sine of theta. And for mathematical induction, you know, we have our basis step and our inductive step. So with our basis step, since in the problem statement we have n greater than or equal to 2, you want to focus on the initial case of n equals 2. So for mine, I said that using this equation here that I just underlined and subbing in 2, that means, here we go, that means that z squared, or I'm sorry, we didn't use that equation. That's essentially the equation we're trying to show that holds true for the case that n equals 2, but we're actually going to use this equation here and just square it out. So z squared is equal to this whole r cosine of theta plus I sine of theta, all of that squared. And you can distribute that squared essentially to both parts. So the r gets squared, and then this whole inside the parentheses gets squared as well. And then if you square out the cosine and the I sine, keep the r squared, and that becomes cosine squared theta plus 2I cosine theta sine theta plus I squared sine squared of theta. And we also know that I squared equals -1, and I'm also going to move some stuff around a bit, and you'll see why in a sec. So I'm going to rewrite this as r squared equals cosine squared theta minus sine squared theta, because we know that that I squared is -1, and that's plus I times 2 sine theta cosine theta. So that's where we're at now. I'm going to go ahead and go on to a new page here. So I'm going to rewrite that so we can reference it. So we're at r squared times the quantity of cosine squared theta minus sine squared theta plus I times 2 sine theta cosine theta. Now once you get to this point, you're going to recognize some trig identities that we've learned. So using trigonometric identities of, we have the identity, the cosine double angle, so we have cosine of 2 alpha equals cosine squared alpha minus sine squared alpha, and we have the sine double angle, sine of 2 alpha equals 2 cosine alpha sine alpha. So using those identities, we can rewrite the equation above, keep the r squared, and the cosine squared theta minus sine squared theta now becomes cosine of 2 theta plus, and then the 2 sine cosine becomes I sine of 2 theta. And it seems like we've already done a lot, and we have already done a lot, but everything we just did was proving the basis step. So I'm going to write a little conclusion for that basis step, and I'm going to say thus z to the n equals r to the n cosine of n theta plus I sine of n theta is true in the case of n equals 2. Thus, we have shown the basis step. So that was the initial case of n equals 2. So that proves our basis step. And now we're going to want to move on to the inductive step, which is going to help us show that it's true for all n greater than or equal to 2 and not just 2. So let me go on to another page here. Okay, now I'm going to start with, as for our inductive step, we will assume that z to the n equals r to the n cosine of n theta plus I sine of n theta. So what you're going to want to do is you're going to make that assumption, and you're going to try to show that this assumption leads to z to the n plus 1 equals r to the n plus 1 times cosine of n plus 1 theta plus I sine of n plus 1 theta. So essentially you're going to assume z of n and try to show that for any n, the next case is true for n plus 1. Okay, from here, well, we know, using our assumption, z to the n plus 1, we know that that's the same as z to the n times z to the 1, right? So I'm going to use our assumption of z to the n and our original assumption of z. So this is the same as saying, subbing in for z to the n and z to the 1, we get r to the n cosine of n theta plus I sine of n theta times r cosine of theta plus I sine of theta. And now you're just going to want to multiply this out and hope that you're seeing some things. So I put together the r's to get r to the n times r, because eventually we can just write that as r to the n plus 1. And then multiplying out this inside, you get cosine of n theta cosine theta plus cosine of n theta I sine of theta plus I sine of n theta cosine of theta plus I squared sine of n theta sine of theta. So it's looking really disgusting now, but we're going to make this look a lot better. So, like I said, r to the n times r is r to the n plus 1, and I'm going to keep that outside, and I'm going to rewrite the inside as cosine of n theta cosine theta minus sine of n theta sine of theta plus I cosine of n theta sine of theta plus cosine of theta sine of n theta. And I was able to once again do that because we know that that I squared is equal to -1, and all I did was move some stuff around. If you need to pause it and see that, you can, but I'll continue here. So at this point, I'm going to go ahead and go to another page so I can show something else that we're going to use. So I'm going to rewrite that really fast. Goes r to the n plus 1 cosine of n theta cosine theta minus sine of n theta sine theta plus I times the cosine n theta sine theta, sorry for the sloppiness, plus cosine of theta sine of n theta. Okay. So now, once again, you should be able to recognize some trig identities. So using the trigonometric identities of, here they're going to be different. They're going to be the cosine sum and the sine sum instead of the double angles. So I'm going to use the identity of cosine of alpha plus beta. Oh my, I don't know why my screen's doing that. Yep, cosine of alpha plus beta equals cosine alpha cosine beta minus sine alpha sine beta, and that the sine of alpha plus beta equals sine alpha cosine beta plus cosine alpha sine beta. So subbing those in, it's going to make this look a lot cleaner. So we're going to get that down to r to the n plus 1 times the quantity of cosine of n theta plus theta plus I sine of n theta plus theta. And essentially, you can keep going with this and just factor out a theta within the inside of that cosine. So you're going to have cosine of theta times n plus 1 plus I sine, and do the same thing here, theta times n plus 1. Right? And that's exactly what we needed. So, here, I'm going to write as needed. As needed. So therefore, at this point, we have shown the entire basis step and the inductive step, because with our inductive step, we were able to start with our assumption of z to the n, and we were able to show that this other case of z to the n plus 1 was now also true. So we've shown the basis step, we've shown the inductive step, so now we can write our conclusion. So therefore, if z equals r cosine theta plus I sine of theta, and n is an integer with n greater than or equal to 2, then z to the n equals r to the n cosine of n theta plus I sine of n theta. And there we go. So that concludes that proof. It took me a bit. I thought it was pretty interesting to figure that out using those identities. And it's a really neat proof. If you have any questions on any of the logic I used, feel free to reach out to me. But I hope this makes a lot of sense, and that this helps you with finishing up number 4 on the homework. Have a good rest of your weekend.